This is section 5.1, and we're going to look at isosceles triangles. So the learning goal that we have for this lesson is that students will understand the properties of isosceles triangle, and then we'll use those properties to make conclusions. So let's talk a little bit about isosceles triangles to make sure we're all using the same language and know what we're talking about when we use these words. The parts of an isosceles triangle that you need to know are the legs, the vertex angle, the base, and the base angles. So the legs are the two congruent sides. So I'll try to, let's see, show you what I'm talking about as we go through this here. So the legs are the two congruent sides. You can tell by the markings in this picture that these two sides here and here are the legs. Now the vertex angle is the angle between the two legs, or in other words, the angle that the legs form. So remember, these were my legs here and here. So the angle that those two legs form is right here. So this guy is the vertex angle, and it happened to be on the top of my triangle, but that doesn't necessarily need to be the case, right? Our triangle could be upside down, and now my vertex angle is here. So pay attention to the orientation of your figure. Is it upside down? Is it right side up? Where are the legs? Where is the vertex angle? And the base is the side that connects the two legs. Again, don't think about the base as being the bottom. Think about it as the side that connects the two angles. In this case, or excuse me, that connects the two legs. In this case, it happens to be on the bottom of the triangle. But if my isosceles triangle was rotated like this, now my base is at the top of the triangle. And then, of course, the base angles are the two angles that are attached to the base. So if this is my base down here, the base angles would be here and here. And of course, those are highlighted in red. So these two guys are my base angles. So using the correct terminology is really important when we start to discuss the properties and the theorems of isosceles triangles. Okay, so here's the first theorem, the first idea, first property we're going to talk about, the isosceles triangle theorem. The isosceles triangle theorem says that the base angles of an isosceles triangle are congruent. So, a couple of things that we have to have in order to use this theorem. The first is an isosceles triangle. We need to know that my triangle is in fact isosceles. So, here's my triangle over here. If we knew that AB was congruent to CB, we knew this side was congruent to this side, then we would know angle A is congruent to angle C. Excuse me, little sneeze there. Okay, so then we know angle A is congruent to angle C. These two angles have to be congruent. So this is what we call a conditional statement. We're making a condition. The condition is my triangle is isosceles, or the condition is that side AB is congruent to side CB. And the result is that angle A is congruent to angle C. All right, another way of saying this, of course, and not in a conditional statement, is that those base angles are going to be congruent. All right, the next theorem that we want to talk about is the angle bisector theorem. So let's break down the language that we see here. The bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. The bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. So let's break this down and see what this is talking about in the diagram. First of all, we need to know if we have an isosceles triangle. So let's assume we know that side RS is congruent to side ST. So now we have an isosceles triangle. The base then of this triangle would be the side that connects those two legs. So RT would be the base. The vertex angle would be the angle that connects the two legs. So angle S is the vertex angle. So this says the bisector of the vertex angle of an isosceles triangle. So what we need to do is bisect that vertex angle. In other words, we need to cut it in half. We need to bisect that angle. So if we cut this angle exactly in half here, just like this, so now we know that, let's say this angle here is congruent to this angle here because we cut it in half. If we do that, then that bisector is the perpendicular bisector of the base. So that tells us two things. First, it tells me that it makes a 90-degree angle with the base. Second, it tells me that it cuts that base in half. So let's label this, I don't know, point M or something like that. If we make point M right there, now we also know that RM is congruent to MT. So let's write that down. RM is congruent to MT. Great. Another conclusion that we made is that angle SMT is a right angle. Now, how did we know that was true? Well, that was only true if angle RSM was congruent to angle TSM. So if angle RSM was congruent, oops, to angle TSM, then we know that RM is congruent to MT and that SMT is a right angle. Okay, so if we cut the vertex angle in half, that segment has to be perpendicular to the other side, and it cuts the other side in half as well. Let's do a couple of examples. So example one, let's find the values of x and y. So here we see a triangle, and we see that it has two sides that are definitely congruent, and I need to find x and y. Now let's pay attention here. I notice that these two angles at the top are congruent. That means that this segment here is the perpendicular bisector of the opposite side. Well, that means that it forms a 90-degree angle. So I automatically know that y is equal to 90. It has to be. Okay, so now let's look at the problem in maybe a simpler way. We still need to find x, right? Well, we know that this angle here is 51 because this angle was 51. We see the two sides that are congruent are here and here. Those are the legs. So the base angles of my isosceles triangle have to be congruent, therefore they're both 51. Okay, so now I can maybe make the problem a little bit simpler. Let's highlight what I want you to focus on. Let's look at this green triangle right here. I'll try to be neat, but I can't be that neat. You guys be neater if you can. Let's highlight that green triangle right there. Now we know that this angle is 90 degrees. We also know that this angle is 51 degrees. So if I wanted to find x, all I have to do is add 51 plus 90 and subtract that from 180. So let's see, 51 plus 90 is equal to 141. 180 minus 141 is equal to 39. So x must be equal to 39. And we're done. Okay, now let's make sure that makes sense. Does this look like it could be a 39-degree angle? That looks reasonable. And then if this angle was 39, then we could also say that this angle over here was 39. And then we could make sure that all of these angles added up to 180 as well, because that's also a great big triangle. Now I know my picture's getting a little confusing, but we can talk more about that in class on Monday. Let's do another example. Let's say we wanted to find the values of x and y in this case. So here, notice in my picture, I know that these two angles are congruent. That must mean that these two sides are the legs, right? Okay. And I also happen to see that this is a 90-degree angle. So that means that this segment that I see here must be the perpendicular bisector. And it must also bisect the vertex angle up here. Well, that's good information because that means if this is 23 degrees, then this angle here is also 23 degrees. And knowing that is going to allow me to figure out the values of x and y. Let's think about what this whole big angle is. If each of those are 23, 23 plus 23 is 46. So this vertex angle here must be 46. Now we also know that this angle here is x and the other angle is y. But since those are the base angles of this isosceles triangle, x and y have to be congruent, don't they? So I'm just going to, instead of y, I'm going to say, whoopsies, I keep erasing it. There we go. I'm going to say that this other angle is also x because they're really congruent to each other. X and y are the same. So we'll say that's x, and this is 46. So all I did was redraw my triangle without that perpendicular bisector in it just to make the problem a little bit simpler. So an equation that we can set up is 46 plus x is equal to 180. Or 46 plus 2x is equal to 180 if I simplify. If I were going to solve that, of course I'm going to subtract 46 from both sides. And so 46 adds to 0 over here, so we're going to get 2x is equal to 134 when I do the subtraction. And then of course I would divide both sides by 2, and I would get x is equal to 67. But of course if x is equal to 67, y is also equal to 67 because x and y were really the same value. Okay, so one other idea that we haven't really talked about, but we just used in that case, was what we call the converse of the isosceles triangle theorem. And a converse switches around the if-then statements. So if you recall, let's just take a second. You guys can look back up in your notes, but we'll just go back to this page here. The isosceles triangle theorem said, if I know that these two sides are congruent, then I know that the base angles are congruent. So if the sides are congruent, then the angles are congruent. The converse switches that around, and it says, if I know the angles are congruent, then I know that the sides must be congruent. And so that's what we're saying here. If angle A is congruent to angle C, then I know that side AB has to be congruent to side CB. So our converse is just going to say, if the base angles are congruent, then I know that the sides have to be congruent as well. So in my little diagram, if I know these two angles are congruent, I can make the conclusion that these two sides have to be congruent as well. Okay? So let's use that little piece of information to help make some conclusions. Let's complete each of the congruency statements, and then let's talk about how we know that that has to be true. So let's inspect the diagram for a second. Here we have several triangles. We actually have one big triangle and then two smaller triangles inside the big triangle. And what my diagram indicates is that angle F is congruent to angle EGF. And that angle is also congruent to angle IGH, which is congruent to angle H. So all four of these angles here are congruent. All right, so let's see if we can't answer the questions here and complete the congruency statement. First, we have side DH. So side DH is this whole big side. Now, I think your gut is probably going to tell you that side DH is going to be congruent to side DF, right? Those are the two corresponding sides. They have the same length, DH and DF. But we know those sides are congruent because we know that angle H is congruent to angle F. So that's how I can make a justification for this. These base angles are congruent, so therefore these two sides are congruent. So let's do the next one. Side HI, which is here, has to be congruent to side GI. So we'll fill that in here, side GI. And again, why do you know that that's true? How do we know that these two sides are congruent? Because their base angles are congruent. Now in this case, we have to be a little bit more careful about how we write that congruency statement. We can say angle H because it's the only angle there, but we have to name the other angle. We can't name it angle G because there's 3 different angles at angle G, so I have to call it angle IGH. All right, so the reason that I know HI is congruent to GI is because angle H is congruent to angle IGH. All right, so one last one here. Side EG is congruent to, so EG is here, that's going to be EF. So side EG is going to be congruent to side EF. Now how do we know that's true? Of course, because these two angles are congruent. And again, we have to be careful about how we name that second angle. We could say angle F because it's the only angle there, but the other angle we have to name with its 3 points. So angle FGE would be the second angle, or you could call it angle EGF. That would work as well. All right. So one final example here. Let's look at how do we put some algebra in here. So let's say given all of this information we want to solve for x. So let's see what we know here. We know that side AB, the length of side AB is equal to 3x minus 2. So let's put that in my picture here. And we know that this length of side BC is x plus 4. And we know that the length of side AC is equal to 7. Might have drawn my picture a little bit weird here now that I'm looking at it. That's okay, this will be a good thing to discuss. And we know that side AB, be careful here, side AB is congruent to side BC. Okay, so this is where I may have made a little mistake when drawing my picture originally. I didn't really draw it to scale. Notice which two sides are congruent? BC and AB. So we have to mark it that way. The way I drew it, it looks like these two sides are congruent. But according to the information, I know that AB is congruent to BC, which makes my picture look a little funny. So maybe you can draw your picture better so that it looks like those two sides are congruent. But that's a good thing to think about because sometimes our diagram might be drawn so that it appears that two sides are congruent, but that's not what the information tells us. So go by what you know, not by what the picture looks like and that you assume is true. Okay, so our goal is to solve for x here. Obviously, since these two sides are congruent, I'm going to start by setting those two lengths equal to each other. So I'm going to say 3x minus 2 is equal to x plus 4. And we're just going to solve that equation for x. I'll subtract x from both sides because it's the smaller of the two x terms. So that's going to give me 2x minus 2 is equal to 4. And then, of course, adding 2 to both sides, it's going to give me 2x is equal to 6. And then if 2x is equal to 6, and I divide both sides by 2, we will get x is equal to 3. And if I plugged that in here, 3 times 3 is 9. 9 minus 2 is 7. So this side would be 7, and that side would be 7 as well. And it's along the same scale. And actually, it would be an equilateral triangle because all 3 sides would be 7. All right, one final thing to talk about, and that is this corollary. Remember, a corollary is something that follows from a theorem. It's something that's directly concluded based off a theorem that we've talked about. So in this case, the theorem was that the base angles of an isosceles triangle are congruent. So a conclusion that I can make from that is that if my triangle is equilateral, then it's also equiangular. In other words, if all 3 sides of my triangle are congruent, then of course all 3 angles of my triangle have to be congruent as well. And that's probably you're thinking common sense, but what we're doing here is proving it and or saying that it can be proven, in fact, that all 3 angles have to be congruent. And so we'll talk about a way to prove that in class. Okay, so what I'd like you to do now is stop and go back and fill in some of the questions for your left-hand column. Summarize the theorems and informations that we've talked about. Make sure you discuss the isosceles triangle theorem and the angle bisector theorem and the conclusions that you can make from that in your summary.